how do you like the ketchup to flow, or how do you like the sauce to flow? So in our daily life, we use the ketchup or the tomato ketchup, tomato sauce, or the chili sauce. We pour on our plate or the food. So how do you actually like the sauce to flow? So liquid food products should be formulated to display certain desired rheological behavior. For example, easy to pour from the bottle, but flow in a controlled manner and recover the viscosity upon pouring on the plate. So if you remember this from the notes, this is my son pouring this is actually a plum sauce, and this is actually a tomato sauce or tomato ketchup. And depending on the type or the brand, you can see some actually is quite easy to pour, or some actually you have to tap on the bottle, then it will pour. And once you pour it on the food or on the plate, you can see actually if you leave it for some time, it will start to spread. But some actually spread less, or some actually spread more. So it depends on the type of the product. So that's actually the problem, the questions that I have given you in the test. So the problem is the figure below is actually a flow curve, but in this case, there is actually a plot of viscosity against the shear rate over a range of shear rate here. So we have two samples, sample A and sample B. So it shows then you get a two flow curve for two brands of tomato sauce, sample A and sample B. And you are informed that both samples have almost the same value of yield stress. So this is something that you have to pay attention here. The same value of yield stress. So you can see here the starting point had a low shear rate. Both sample and A and B here. A is actually the continuous line, and B is actually the dashed line. But both actually start more or less at the same point, which means that they have more or less the same yield stress. Yield stress is actually the minimum stress, or the minimum force that we require to initiate flow. So it means that both sample A and B would require the same initial stress or force to initiate the flow, to start the flow. So this is actually a very important information here. Okay, so let's see what's the questions. The question is, what type of flow behavior shown by sample A, and what type of flow behavior shown by sample B? So actually sample A is a pseudoplastic behavior, which means that it displays or exhibits shear thinning behavior and time independent. What does it mean? It means that once it starts to flow, so it starts from this high initial viscosity, but when it starts to flow, the viscosity actually will reduce as we increase the shear rate. So you can see from the curve here. So it means that this is what we mean by shear thinning, because once you increase the shear, the viscosity will reduce, become thinner, and it will flow more readily. So time independent, it means that the viscosity at any constant shear rate, if you fix any, at a constant shear rate and you stir the sample at a fixed shear rate, but as a function of time, and the viscosity will remain constant. That is time independent. So when the material shows a time independent behavior, it means that when we carry out the experiment and we determine when we increase the flow curve, so we get one curve. This is what we call up curve. Up meaning that when we increase the shear rate, then we get until to this point. Then after that, we reduce the shear rate. We remove the shear rate, and the shear rate will start to decrease. But for pseudoplastic, what we will observe is the viscosity actually will kind of recover almost like immediately. So meaning that it doesn't depend on time. The viscosity actually will recover, the structure actually will recover very fast to the initial viscosity. So that's the meaning of shear thinning, time independent. It doesn't depend on time, because once you remove the stress, it will recover the viscosity very fast, almost immediately. Whereas sample B, I'm sorry about that, that is actually the notification. Sample B is actually a thixotropy. Both sample actually are shear thinning. Pseudoplastic and thixotropy is both are shear thinning, because when we increase the shear rate, the viscosity will decrease, will reduce. So it's shear thinning. But then the difference is once we remove the shear stress here, the recovery of the viscosity here will take time. So hence time dependent. So you can see here the first curve, which is the up curve when we increase the shear rate, and the down curve when we decrease the shear rate does not overlap. You can see some area between, or we call it hysteresis, between the up and the down curve. When we get this situation, then we can say that this sample, in this case sample B, exhibit thixotropy, shear thinning, but time dependent. It means that the recovery of the viscosity to the original viscosity will take time. Okay, so the reason, the difference, because the reason I will explain to you later, but I think this is actually clearly shows the difference in the pseudoplastic and the thixotropy behavior. Okay, now next questions or problem based on the same graph. Which sample is expected to be readily pourable from the bottle? Which one is easier to pour initially from the bottle? Briefly explain your answer. Well, both actually have the same yield stress, meaning that initially both actually will have the same resistance to flow, because the yield stress is actually about the same. So we cannot really differentiate. But once it starts to flow, you can see here, sample B, once it starts to flow, it will actually, the slope, look at the slope here. The viscosity actually drop more drastically compared to sample A. Look at this curve. So it means that the viscosity reduce much more faster compared to sample A. So at any point, if you take at any point of the shear rate, okay, we take at any point of the shear rate, let's say at this point, okay, at this point maybe they flow more or less at the same rate. But once you get to this point, at this shear rate, you can see here the viscosity of sample B is actually much lower than sample A, and here is at higher shear rate is even more. So meaning that sample B actually is thinner and should actually flow more readily or more easily. Okay. Now, next question is, which sample is expected to spread less on the plate? Briefly explain your answer. Spread less. So the answer is actually sample A. Why? If you remember, this is from the notes. Sample A, sample B. So, but in this case, the flow curve is actually shear stress on the y-axis and shear rate. And you can see sample B, which has higher hysteresis. So this one is more, actually is thixotropy, this is more like pseudoplastic. Okay. So thixotropy, remember, thixotropy is time dependent. So at this point, the viscosity is actually lower than the initial one, and it takes time to recover the viscosity, while sample A, which is pseudoplastic time dependent, will recover almost immediately. So the sample B will take time to recover the viscosity, so it will actually, while it is recovering the viscosity, it has time actually to spread more. Whereas this one, it recovers the initial viscosity, so it doesn't have much time to spread, because it has recovered the viscosity very fast. This one is slower to recover the viscosity, therefore it has more time to rebuild the structure. So you can see that, for example, we can see that because of the slow rebuilding of the structure after shearing. Sample B actually shows a slow rebuilding of the structure, and therefore it will have time to flow and spread more compared to sample B. Okay. So suggest one ingredient in the tomato sauce that give rise to the difference in the flow curve profile. The difference would be in the, usually the type of high molecular weight polymer that you have in the sample. For example, maybe the type of hydrocolloids or gums or stabilizer that we add. So for example, here you might have like xanthan gum. Maybe here you have a modified starch. So xanthan gum is actually known to have kind of ability to rebuild the structure faster. It will recoil, the polymer kind of will, like you stretch rubber band, and the rubber band will actually back to the, to the original shape very quickly. Whereas for sample B, maybe a different kind of hydrocolloid, which have less ability or slow to recoil or to rebuild the structure. So the type of hydrocolloid that we add in the two sample here might be different, and that actually will give different with, in terms of the flow behavior, whether it will show a pseudoplastic or thixotropy behavior. Next question is, suppose two types of chocolate drink display the flow curve in figure 1. So in this case, it's not tomato sauce, it's a chocolate drink. So which sample will display greater stability towards sedimentation during long-term storage? Now, the keyword here is long-term storage. Storage, when we store the product, on the shelf, actually it's actually subject only to gravity. So it means that we are looking at the flow curve or flow behavior at low shear rate. We are looking actually here on this zone or region where the shear rate is very low, because the only stress acting on the sample during storage is actually gravity. Okay, so so knowing that we are looking in this region, so if we look at the viscosity here, we are looking at the viscosity here, and initially if you read the question just now, remember it has the same value of yield stress, which means that we need the same initial force or stress to initiate flow. So in this case, because of they have the same value of yield stress, so we can say that both sample A and B will show more or less the same stability towards sedimentation. Okay, it's not A, it's not B, but both, because they have the same value of yield stress. So okay, I think that's, I hope it is clear, the answer, and how do you interpret the information that you get from the flow curve. In this case, differentiating the type of flow behavior, whether it's pseudoplastic, shear thinning, time independent, or thixotropy, shear thinning, time dependent.